So I am very pleased to introduce Catarina, and I think Wally will be joining to talk about SU2-NEMO. This is an open source framework for non-equilibrium flows. They've been a very active group, both on GitHub, publishing. These folks have been at the previous conference showing a lot of good work. So I'll kick it over your way, Catarina.
Okay, can you see me? Okay, I can see me. Hi, Tom. Thanks for introducing me.
Of course.
So if I try to build this up. So I would like to start the presentation by explaining that SU2-NEMO actually started from a collaborative effort between different people from different institutions with different areas of expertise. So on one hand, we have universities of Strathclyde and Stanford that focus more on the aspect of numerical and computational implementation, but also have done a lot of working to try to understand better the physics of hypersonic flows. Then we have von Karman into the fluid dynamics and University of Arizona that to focus more on the physical modeling of the non-equilibrium phenomena. And we also have INRIA that basically specializes in automatic mesh adaptation with anisotropic meshes. So to give you a bit of an idea of what kind of research SU2-NEMO is actually being used for, at least at the moment. So we have some work that focuses on better understanding interaction patterns between shock waves and between shock and boundary layer on arbitrary mixtures of gases. Then we have also been working on better understanding the aerothermodynamic environment that occurs during re-entry in the process of fragmentation. So basically what happens when we have multiple bodies entering the atmosphere. And both of these topics usually we tend to use more canonical geometries since we are focusing more on the fundamentals. However, then we also have some work that simulates more realistic 3D vehicles, high-speed vehicles, to understand how these will differ from the more canonical geometries. So next slide. Okay. So this is the outline that is going to be followed during this presentation. So we are going to go through this. Yeah.
Sorry to interrupt you. The video and audio is a little choppy. I would recommend maybe just turn off your video and just go with audio.
Okay, let's try.
Thank you. Yeah.
Okay, let me know if there's any other issue. Okay, so this is the outline that we will follow during this presentation. So we're going through the different topics of research that we're currently focusing on with SU2-NEMO, and we will conclude with outlook and perspective for future work. Okay, so on the topic of shock interaction phenomena, we are aiming at further understanding the interaction patterns that occur in this type of flows for mixtures that are actually different than air. And we're going to present some work that we did when it comes to comparative analysis of different ways of modeling the vibrational energy relaxation and the impact of the different models in the actual obtained shock interaction patterns, but also the loads that occur at the surface of the bodies. So we're comparing the more simplified thermally perfect gas model that basically considers that the increase that we have in internal energy of the flow across the shockwave is redistributed instantaneously from the translational degrees of freedom of the molecules to the vibrational degrees of freedom. So this means that thermal equilibrium is actually being enforced, and therefore we only need one temperature to describe flow physics. On the other hand, we consider a more detailed thermal non-equilibrium model, the two-temperature model, and this model accounts for the fact that actually the process of energy redistribution is not instantaneous. Instead, it takes a certain amount of time to relax until reaching a state of thermal equilibrium. So basically, we need two temperatures, translational and vibrational, to for the possibility of thermal non-equilibrium. These are some of the results that we have obtained for Mach 9 CO2 dominated flow over a double wedge geometry, in this case, the 1540-degree angle. So these are results for counters of temperature. And basically, we can see that for both models, so using the schematics here that basically reflect the flow features of the numerical results, we can see that for both models, we obtained what is called a type 6 Edney interaction. However, the overall interaction mechanism is different, and this is actually due to what is happening near this compression corner here. So what's happening is that in the non-equilibrium model, because the internal energy across this first shock wave goes completely to the translational degree of freedom before being distributed, this means that we will need a stronger shock to decelerate the flow, to deflect the same angle that it would in the thermally perfect gas model. Because in the thermally perfect gas model, a portion of the energy goes towards the vibrational excitation instantaneously. So we can have slower flow after this first oblique shock. We also have a thicker boundary layer that we can see over here that separates and creates a larger separation bubble. Here we also have a separation bubble, but it's very small that almost cannot be visualized in counters. So here we will have a detachment shock associated to the separation, whereas here, because of the larger size, we also have a reattachment shock, and this is basically the main difference between the two mechanisms. If we look at the distributions of pressure and heat flux along the surface of the wedges, we can see that in the case of the Nonequilibrium model, we have the increase due to separation and then the reattachment shock, whereas in the thermally perfect gas model, we only have a large peak of the detachment shock. However, looking at the heat flux distribution, we can see this small decrease in heat flux, and this is basically what reflects small separation that cannot be visualized in the columns. This is the same set of the results, but instead for a 1550 geometry. So basically, we are raising the angle of the second wedge. And here we see a similar behavior to the previous geometry. So we obtain a similar type in both models, which is in this case a type 5 Edney pattern. However, due to the significantly different sizes of the separation area in compression corner, we have a different shockwave system close to the sphere. The detachment and the reattachment shock always remain below the leading shock that interacts directly with the bow shock in this triple point, whereas in this case, so we have again slower flow and stronger detachment shock that crosses the leading shock and only then interacts with the bow shock in the triple point. So we have, let's say, an additional system of waves that is not seen in the thermally perfect gas model. Again, this is reflected in the distribution of loads on the surface of the double wedge. So here we don't have only the raising pressure due to the separation and the one due to reattachment, which is basically the first peak, but we also have a second peak that is due to the impingement of this shock right here on the surface of the second wedge and the equivalent here as well. And we can basically notice that for the thermally perfect gas model, these peaks tend to be larger and occur at an earlier location than for the non-equilibrium model. Now, on the topic that is more related to the study of fragmentation during reentry, in SU2-NEMO, we were wanting to be able to simulate not only the continuum regime, but also to simulate more rarefied flows. And so basically, the transition between slip and continuum regime, what happens is that the velocity and temperature of the gas are not equal to the velocity and temperature of the wall, because basically there are no sufficient particle collisions in this region, which invalidates the commonly used no-slip approach. So we could properly simulate the transitional regime and solve the Navier-Stokes equations accounting for this. We implemented a simple Maxwell slip velocity and small Bovsky temperature equations in SU2-NEMO that are shown here. We tested this for the case of flow of diatomic nitrogen for two different Nansen numbers. So we have here 0.01 and 0.05, showing the counters for temperature. And in order to, let's say, verify or validate these results, we compare pressure coefficient and heat flux coefficient to results obtained with DSMC with the solver called Monaco, and we see that overall a very good agreement is obtained. Okay, so to again simulate a test case that tries to mimic what happened in fragmentation, we have simulated multi-body test cases that are shown in the slide at the left. So here, and in this type of situations, shock interactions is also a phenomenon that tends to occur, but in this case due to the presence of several objects. And shock interaction will have an important role in the dynamics and in the aerothermal loads of the object downstream, because we have the bow shock here interacting with the bow shock of the second cylinder and resulting in a certain interaction. And often the pressure and heat flux loads that are very severe and localized in the second cylinder can be enough to initiate the fragmentation process. In this work, we did a comparison between different types of grids. So basically, we used mesh-based anisotropic grid adaptation with AMG that is shown at the bottom. This type of adaptation allows us to have highly stretched elements that follow better directional features when compared to the case of purely isotropic adaptation that in this case we did with the Darwin solver. So if we go to the next slide and we zoom in the interaction region, we can see, comparing the different adaptation processes, that actually AMG provides a much better capture, especially when it comes to this continuity that we see in the last mesh here. And in the counters, it's the contact continued. So having assessed the capability of SU2-NEMO to properly use isotropic meshes for two-dimensional cases, then we went to the case of 3 dimensions. So we simulated proximal spheres. And once again, these results highlight the importance of using an adapted grid that follows well the directional features. So if we compare again Darwin to AMG, we see not only that the shocks are much better, they're much finer. And if we zoom in the interaction area here, we can also see that the impingement of this jet is also very well captured, which at the end of the day is the most important thing for vehicle design. So now I'm going to pass the word to my colleague, Walter Maier.
Hi, everyone. I hope everyone is doing well. So to continue on with what Catarina has mentioned, we'll present some more test cases here that we've run recently. With SU2-NEMO, some of the hardest things to do are predicting surface properties like heat flux and accurately computing flow enthalpy. So this case here represents an arc jet, which is essentially a way to test high enthalpy flows by rotating a electric arc in our plenum and going through a converging diverging nozzle. And this allows us to kind of capture high enthalpy flows. So with this case, we're simulating a flow that has 15.2 megajoules per kilogram of enthalpy. And it's really difficult to capture the enthalpy, particularly along the center line. One of the developments that is directly used in this case is the use of the axisymmetric source terms that one of our colleagues had just implemented. And in this case, what we really want to notice is in the case here, we see the temperature plots. In the plenum and the converging part of the nozzle, we see pretty good equilibrium with the temperatures. However, once we reach the diverging nozzle, we start to see a large discrepancy, a large state of thermal non-equilibrium. When we move over to the species concentrations, we see slight chemical reactions here with N2 increasing a little bit and YN decreasing a little bit. However, in this case, we don't really activate too much of the chemical reactions. And in this case, is more focused on the thermal non-equilibrium aspects of the flow. I'll go to the next slide. Oh, there we go. Another case that we're really looking into is gas surface interactions. So as mentioned before, predicting heat flux in these regimes is extremely difficult. You can use your standard isothermal or heat flux wall. However, once we start reaching these temperatures and levels of enthalpy, they no longer valid due to the fact that we have species recombination at the wall boundaries, particularly the monatomic species like monatomic oxygen and nitrogen will recombine into N2 and O2. So work is being done right now to kind of model these catalytic wall boundary effects. We have some of the equations listed here. And in doing this, some of the things that we're looking into are supercatalytic walls, which is essentially saying all N2 and all nitrogen and all oxygen are recombined at the wall. So there's no more single monatomic species at the wall. We have partially catalytic is where we kind of specify this gamma value here. So we get a more realistic type of recombination. So we're still going to have nitrogen and oxygen at the wall. However, it's not going to be a simplifying assumption where it's either none or all. And the importance of this, it may not seem that large in scale. However, when looking at the surface heat flux, we see that the supercatalytic wall does predict higher heat flux, which is extremely important when it comes to designing TPS systems or thermal protection systems, and making sure if you're designing a vehicle, it doesn't melt, which I think is always a good thing. And then, another area of work is hypersonic turbulence. As of right now, the SA models plus all their versions have been added into or coupled with the SU2-NEMO solver. And there's not much difference between the SA model that's presented with NEMO as in the regular SU2 solver. The big differences kind of lie within the variable structures within SU2-NEMO. So with SU2-NEMO, we are carrying multiple densities and multiple temperatures, which doesn't really line up with the SA model that the baseline SU2 uses. So as for now, we've mirrored those functions over and played around with the indexing information. And one of the important things is the SA model is designed for a single density. So to get around that, for right now, we take density as the sum of all the densities in the flow. We're working through implementing the SST model, as well as looking into some more hypersonic specific models to better kind of understand what's happening there, with the end goal being modeling transition in hypersonics, which is always fun to do. So this case presented here is the NASA TMR axisymmetric shock wave boundary layer interaction, or more funnily known as ASWIBLY. So this is one of the cases that we ran for a recent publication where we were looking into the shock boundary layer interaction, similar to what Catarina had shown above, maybe less drastic with the interactions. And here are some of the results coming out of SU2-NEMO. We're predicting the boundary layer fairly well. We're capturing surface pressures very well. One of the things active work we're looking into is the heat flux calculation, which we see here, where SU2-NEMO is predicting a higher peak heat flux, which is a little also closer to the compression corner. And this may be due to we've added some extra physics but aren't capturing some other parts of the physics, possibly with Prandtl a constant Prandtl turbulent number may not be the most appropriate, but these are some of the things that we're doing and working through with SU2-NEMO. And in the terms of the SST model, we expect to get better results by more accurately predicting the separation region at the compression corner. And with that, that kind of concludes some of the developments that have been made in the SU2-NEMO solver in the past year. We're continuing to build and improve on the code framework, but here are some of the more detailed outlooks and future work that is either ongoing or very near in the works. And some of that includes looking into uncertainty quantification, particularly with the thermochemical models we use, robustness and accuracy on anisotropic grids, gas solid and gas surface interactions with the catalytic wall boundary conditions. A big one that I know is going to cause a lot of headache for some of our future pull requests, but code robustness and speed up. It's always a challenge, and we look forward to updating NEMO. Looking into reintroducing the discrete adjoint, reduced order modeling capabilities, re-entry, magnetohydrodynamics, and most recently, looking into large eddy simulations for SU2-NEMO. And with that, here are some of the recent papers published, so if there's any information more that we can't go over, we invite you to read some of these, but if not, we are happy to take any questions. Thank you very much.
Okay, thanks, Wally. I'd say if you have your camera available, go ahead and turn it on. I'm going to turn mine on. I'll remind everybody that in the GoToWebinar panel, there's a questions area. So if you have questions for Catarina or Wally, excuse me, please drop those in there now. And in the meantime, I'll start you off with a question. I'm curious what exactly you're going to do related to robustness and code speed up.
That's a great question. So not to throw other people under the bus, but someone who's been very helpful in helping us work through that is Pedro. So thank you, Pedro. I think a lot of it is going to be taking a deep look into some of how we do our math, particularly when we equilibrate the temperatures and solve for the temperatures. That ends up being a large amount of time. I believe we use a bisection search at the moment, which really eats up a lot of time and gets a little tricky. So maybe going to a Newton solver, something like that.
Sounds good. Any other questions out there? Please, again, post them in the window if you have them, or if any of the other staff have any questions, you can jump in. We've got maybe another minute for questions.
I see a question from Professor Colonna. So getting validation cases for SU2-NEMO is not very easy. Yeah, I think that's also a struggle. Or I might be able to get a PhD in just looking for these validation cases. A lot of it is classified or just not shown. So we take what we can get.
Yeah, also, when it comes to air, it's a bit more easy, but when we start to go to different mixtures, for example, we have a lot of work done in CO2, and then it gets much more difficult because people tend to focus much more in air and maybe more nitrogen flows, but usually ends there. So yeah, just wanted to add that.
Okay, great. We'll pause there. If any other questions come up, and attendees, please add more questions. We'll